Good day, everyone, or morning, depending on where you are. So, as said, I am Joonas Tikkanen, and I'm working as a scientist at STUK, so the National Nuclear and Safety Authority of Finland. So today I'm speaking about measurement of X-ray machine spectra, or X-ray spectrometry of X-ray tubes. And here in the beginning, I would like to note that the term X-ray spectrometry can also refer to measurement of, for example, of characteristic radiation, so some type of material analysis. So just to make clear that I am not talking about this now, and if you use the term later on, you know the difference between these two. But now I'm talking about measurement of these X-ray tube spectra. And what is the spectrum? So now if we talk about photon fluence or flux spectrum, it means how many photons are coming at each energy to some point in space, or in other words, the energy distribution of the photons. And this distribution, it can be measured from an X-ray machine, but not directly, so to speak. So if we measure with the spectrometer that you can see on the right in the slide, it requires further processing. And a little bit about why we want to do that. The reason is that there are a lot of applications that need the measurement of these spectra. For example, if we are calibrating a radiation protection dosimeter, how do we know that the reading of the dosimeter is right? Or if we make a calibration, what is the actual dose rate in sieverts, so to speak, that we are measuring? I think the most common way is to measure air karma with an ionization chamber, and then use these conversion coefficients from dose air karma to dose equivalent to get the dose equivalent or the operational quantity that we need. And for low X-ray tube voltages, the ISO 4037 standard says that these conversion coefficients need to be determined from experimental fluence spectra. So you need to measure your spectra in essence. Then you can also use the spectra for different correction for attenuation in air. For example, you can calculate these corrections for free air chambers or do correction for attenuation of the radiation in air to NTP conditions for these low voltage qualities. Then there are a lot of other applications, detector development, different research purposes. But the question why the spectrum is needed is really this. We get most information about the radiation from these spectral measurements. So what type of photons with what energies is coming to the point of measurement when we are measuring something. These are the steps you need to do when you are determining your fluence spectra from your X-ray machines. But before we go into more detail into this, let's take a look at the basic physics behind all this. So the X-ray spectrum, how are the X-rays generated? I will go through this briefly. Gavin might have some more detail into this, but in essence, electrons are accelerated in a electric field, and they are collided with the anode of the X-ray machine, which is usually made of tungsten or some other heavy material. And these electrons, they have energy of the acceleration potential times the charge of an electron. And when they hit the target, they produce photon radiation through bremsstrahlung radiation. And that means that the photon energies can be between 0 and the maximum energy of the electrons. And then there is another method through which the radiation is produced. That is the characteristic X-rays from the tungsten, which means that after an ionization in the inner energy shells of the tungsten atom, there is emission of these characteristic X-ray photons. And for this to happen, the electron energy must be above the KH energy of tungsten, which is approximately at 70 keV. And then before we measure the spectrum itself, the spectrum attenuates inside the anode actually, then in the tube window and in the filters. So here in this picture, you can see multiple different spectra. This line A here, that is the spectrum of the photons generated inside the atom. So what photons are born inside the anode. But because the anode is of heavy material, tungsten, not all of the photons reach even the surface of the anode, and it gets attenuated inside the anode. And this spectrum B here is the spectrum that is coming from the surface of the anode. And then we have the tube window, inherent filtering, and the additional filtering, and the spectrum changes its shape the more we attenuate it, and also depending on what material are we using. And here are a couple of different example spectra. So this is, I think, RQR3 radiation quality. So these spectra have this kind of broad shape usually, depending on the spectrum. And this is, I think, is the RQR6. So here the tube potential is 90 keV, which means that we are getting these characteristic X-rays that you can see at the 55 to 70 keV. But one thing about these X-ray spectra is that these are continuous spectra. So we are getting photons with all the energies from the inside the anode from 0 to the maximum energy, but outside the anode practically from some minimum energy up to the tube voltage, so to speak. Then when we are measuring the spectrum, we need some spectrometer with which we measure the spectra. And for this purpose, semiconductor detectors are, I think, solely used at the moment. So the most common one is the germanium. It has multiple good sides, for example, a good photon absorption, very good energy resolution. It's I think the best that you can get with pretty much any type of detector. And also you can get it in large crystal sizes, which here is not that important, but it is possible. But the downside is that it has to be cooled down, which is done with liquid nitrogen, so 77 Kelvin or electric cooling. So it really needs to be cooled down to very low temperatures so that it can be used. But another option, I'm talking today mostly from the germanium point of view, so to speak, but another material that you can use, semiconductor material that you can use is cadmium telluride, which has a very high charge number, which means it has very good photon absorption. And it can be used in room temperatures, or you can cool it down slightly. It also has quite good energy resolution, but when you go to higher energies, it starts having problems due to multiple reasons. And also it's a bit difficult material, and nowadays at least it's available only in relatively small sizes, which again for these low energy measurements is not a problem, but when you start going to high energies, then it can be. How these semiconductor detectors work. So the idea is that when a photon interacts inside the semiconductor material, it creates a secondary electron, which in turn it excites the electrons inside the material from the valence to the conduction band and creates these electron hole pairs, which can be considered as free charges inside the semiconductor material. So it's very similar to ionization in air. And then when you apply an electric field inside the semiconductor, the field collects these free charges. And the energy needed to create one of these electron hole pairs is independent of the photon energy. And you get a lot of these different charges, a lot of these electron hole pairs. For example, if you have 10 keV photon, you already get thousands of these electron hole pairs. And the way the spectrometers work is that the charge is proportional to the energy imparted by the photon. So by measuring this charge created, we can measure the energy of the incoming photon. For example, in the case of photoelectric interaction, we can get the photon energy from the size of this charge pulse. Then, how does a measured spectrum look like? So if we now have a monoenergetic photon source, and the photons are hitting a detector, if the photons interact through this photoelectric absorption, so all of the energy is left inside this semiconductor material, we get this photopeak in the spectrum. So it means that on the x-axis, at the energy of the photon incoming, we get multiple counts in this so-called bin, which forms when we measure long enough. We measure a peak in the spectrum through these events. In an ideal world, all the counts would be in a single bin of the spectrum, but in reality it has this slightly Gaussian shape. But then there are other types of other possibilities for the interaction of the photons. So for example, if the photon goes through Compton scattering inside the detector material and this Compton scattered photon escapes, we get this Compton continuum in the spectrum. And these can have, through different interaction mechanisms, pretty much any energy. So it's a continuum throughout the spectrum up to the photopeak energy. But if we capture the scattered photon, then again, all the energy of the photon, original photon, is left inside the detector material, and we also see these events in the photopeak. And then one option, which happens especially for germanium, usually very near the detector surface, is the X-ray escape peak. So a germanium atom might get ionized, and this produces this characteristic X-ray photon that might escape, and we therefore see a peak 10 keV below this photopeak. So this 10 keV is the K-shell X-ray photon energy. And here you can see a simulated spectrum for 60 keV photons. So this is approximately what the measured spectrum would look like. But please note here that the y-axis is on logarithmic scale, so the photopeak really dominates the spectrum, but we do see counts on all the other energies also. And now, if we start measuring these X-ray tube spectra, what we first need to do, we need to do the energy calibration. So this experimental spectrum or the measured spectrum, it's divided into these bins. So this upper picture is what we get from the spectrometer itself. But now we need to somehow tie this bin number into the real energy. So we can do this by radionuclide measurements. So if we measure a radionuclide, we know with what energies it's emitting photons. And by using this information, we know that these photons form these photopeaks in the spectrum. And then we can see at what bin did this peak emerge in and use that information for the energy calibration. So convert this bin number into energy. And you need to, when you measure possibly even multiple of these nuclides, you get multiple peaks, and you can use all of these to make a energy calibration fit. It's either a linear or second order polynomial fit that you can then use for your measurements. I have to say that if you need to do very precise measurements, then I think you should use a second order polynomial, but the curve is very close to linear in any case. Here are a couple of pictures from our setup when we are measuring these X-ray spectra. Yes, someone has something to say? Or did someone leave the microphone open? Okay, I guess it's nothing. So here are pictures from our X-ray setup. So one important thing you need to do, you need to collimate the field by quite a lot. Because these germanium detectors, they are usually used for this material analysis where you are measuring very low activities from some samples. So these are not meant for very high fluences. So you need to collimate the field by a lot. So for example, here, I'm not sure if it's visible, but the smallest collimator hole inside, in front of the detector, the diameter is only 1 millimeter. And sometimes you have to collimate even more. But now, when we have measured our spectra, so here is now you can also see a cadmium telluride detector here with a collimation setup in front of the detector part. So now we have measured our spectrum, but what is the problem? So here you can see a simulated spectrum of ISO N25 quality, and it should look approximately like this. But when we measure it, we get something looking like this. So what is wrong here? If you remember how the measured spectra look like, so we are getting counts on all of the channels of the spectrum, even if we have a monoenergetic source. But now with X-rays, we have a continuous source, and we get the same continuum from all of the energies, which are mixed with the actual counts that we want to measure. So we now need to come up with some method to get rid of these so-called extra pulses from the spectrum. And to do that, the first step is to make a Monte Carlo model of the spectrometer. So you need to make an accurate model of the spectrometer. Doesn't matter if it's germanium or cadmium telluride. And to do this, you have to use multiple different sources of information. So manufacturer data works up to some point, but you should always be dubious of that. Then you can take X-ray images of your detector. And I think some manufacturers also, you can buy the Monte Carlo model from them, but I don't have any experience of how accurate those are. But I would guess those should work quite well if you want to save some time yourself. But when you are modeling the spectrometer, the front of the detector is most important when we are interested in the low energies. So the window of the spectrometer, electric contact, and the dead layer. So there is this inactive layer of material where we are not collecting the charge on top of the germanium or cadmium telluride. And then when we have the model, we need to validate it somehow. So check that it's realistic, so to speak. So for this, we can again use radiant sources with calibrated activity. And what we can compare then is we can, in the same geometry, make a simulation of the same source that we measured and compare the detection efficiency. So how many of the emitted photons we are detecting in the photopeak of the spectrum. And also we can compare the spectrum shape. So this first one is the so-called efficiency calibration. So do not confuse this with the energy calibration. With energy calibration, we can use any geometry and so on, but this efficiency calibration is a lot more difficult to do. And here I listed just a couple of nucleus that we are interested in because we are looking at low energies. So for example, copper 57, americium 241, iron 55. But the problem really is if we want to be looking at, in the extreme case, spectra with tube voltages of 10 keV, getting these calibration points at the low energies is quite challenging. And how do you do these Monte Carlo models? So you can use multiple different software, Penelope, EGS NRC, Chart4, MCMP, anything that has this capability of simulating the actual spectrum that your detector measures. And at this point, when you are doing this validation of the Monte Carlo model, this can be easily done with a laptop, so it doesn't require too much computational power at this point. And just a note about cadmium telluride, simple Monte Carlo of radiation transport might not be sufficient due to some charge collection issues inside the detector material, but I won't go too deep into this, but this is just something, if you want to use a cadmium telluride detector, that you should keep in mind. And now, when we have the Monte Carlo model, what do we use it for? So now we can do these response simulations. So the idea here is to simulate the detected spectrum or the response of the detector in the whole energy range we are interested in. So now we can use a source that is a parallel beam. monodirectional monoenergetic. Sorry, are you hearing me?
Yes, we are still there. We are still there. Yeah, no problem.
Okay. Okay, now yes. So you use a monodirectional monoenergetic source that is pointing through the collimator hole, which has, and you make separate simulations with source energies from 0 to this maximum energy that you want to use in constant intervals. For example, if you want to have 1 kV intervals, you simulate with make simulations with energies 0.5 kV, 1.5 kV, 2.5 kV up to some maximum energy. For example, 99.5 kV if you're interested to measure up to 100 kV. And this bin size needs to be quite small. If you are looking at these low voltage qualities, for example, in our calculations, we use mostly 0.2 kV intervals, which means that you need to make quite a lot of different simulations. And this result is the response of the detector for monoenergetic photons at each bin of the measured experimental spectrum. And just as a note, you have to do electron transport also if you want to be precise in your simulations. And as a note that, of course, if you need to do some 1,000 different simulations or something like that, of course, you run them with a, you run the simulations and collect the results with a script. So not necessary to do all this by hand. And these results, these can be gathered into a matrix. So in essence, this is just a way to gather your data in a convenient way, and also for one reason that you'll find out a bit later. So each column of the spectrum is the one simulation result or one simulated spectrum of the detector, and you just gather these in increasing order of the source energy. And from computational power, these response simulations you can do with a tabletop computer. I would not recommend a laptop. You can do it, but it takes a long time, and also your laptop starts suffering a little bit if you do a lot of these different simulations with it. And of course, a cluster is always nice, so you can run these simulations faster. Okay, so now we have these response simulations made. So how do we get from this to the actual full-length spectrum? So now we need to apply this unfolding procedure, and there are a couple of different ways to do that. The first is calculating this inverse response matrix. So previously I talked about this response matrix. If you gather these simulation results into a matrix, so now if you kind of in an intuitive way try to think about it, so this S here is now the message spectrum, and this M is the response matrix. So you get the message spectrum by multiplying the fluence with the response of the detector in a kind of superficial way of thinking. So from this, just by matrix arithmetic, you can see that you can calculate the fluence from the message spectrum by the inverse matrix of the response matrix. So inside the software, it is very easy usually to do the calculation of this inverse matrix, but the question is that is the software able to do this inversion and so on. So far, at least for the data that I have seen, MATLAB is able to do it, and also I think Python was able to do it also. But another method is this peeling method. So now, if we look at the message spectrum and the highest bin of the spectrum, so now you remember when we have monoenergetic photons coming in the detector, it has some type of response. Here it is, for example, for the 25 keV photons. So now all of these so-called extra counts are at lower energy than the photopeak. So now if we look at the highest bin of the spectrum, we can say that if the bin size is small enough, we can say that this bin is free from these Compton scattering and X-ray escape events. So it's only full energy absorption events, which means that now we can actually, with this response of this bin, subtract the counts from all the lower bins. So now this deeper blue is now actually the corrected spectrum, and after we did this subtraction, it's not very well visible here, but actually the counts in all of these channels is a bit lower than previously, especially here. If you can see that this 15 keV bin, it's the only bin where it's really visible because that's the X-ray escape peak energy. But even though it's not visible, the same situation applies in all the other bins also. Now, after this, if we look at the second highest bin, now it did have some of these so-called extra events there previously, but they were only coming from the highest bin. Now we subtracted them, so now it also should be only full energy absorption events. So now we can do the same subtraction to all the lower channels. And now you can see at the 14 keV bin that the count is significantly lower in there. And then if we look at the third highest bin, now the same situation applies. And when we continue through the spectrum from higher to lower energies in this fashion and do this subtraction in each channel, now we are getting something that reminds more of this spectrum shape, fluence spectrum shape that we think it should look like. But this is not still the fluence. We get now this so-called corrected spectrum where we only have these full energy absorption events. But this is not the fluence spectrum still. So one more thing we need to do, we need to divide this corrected spectrum with the detection efficiency of the detector. So how many of the incoming photons we are actually detecting in the photo peak. And also because fluence is photons per square centimeter, we need to also divide with the collimator hole area. So to recap, from the measured spectrum with this unfolding method, we get the corrected spectrum, and by using the detection efficiency, we get into a fluence. And this is the so-called end result with which we can do quite a lot of different things. But the fluence spectrum is really what we want out of the measurements, which we can do with this response simulations and the unfolding method. Then I think I'm taking a bit too much time here, but let's talk a little bit about different applications of this spectra. So what we can do and how. We can actually measure the tube voltage from the spectrum, because we know that the maximum energy of the photons coming out from the tube is the kinetic energy of the electrons, from which it's easy to calculate the maximum energy. So for example, here in this picture, we see that the edge of the spectrum is about approximately at, let's say, 29.4 kV. So we know that the tube voltage was 29.4 kilovolts. But this might not be accurate enough for some applications, for example, this ISO 4037 qualities. Then we can calculate the mean energy of the spectrum. It's simply the weight average over the whole spectrum using the weights as a count. We can calculate the width, so find the half maximum value from both sides of the top of the spectrum, and the width is the difference between these 2 points. We can calculate air karma using these mass energy attenuation coefficients. And the idea is that because for monadistinct photons, we can use this equation on the second line. So in here. And now when we look at the spectrum, we can actually think of each bin of the spectrum as monoenergetic photons and apply this equation to every bin. And then from there, we can get the air karma by summing over the whole spectrum. And you can actually talk about air karma spectrum when you do this, apply this equation to each bin of the spectrum. Then we can calculate from spectrum the half value layer, so HVL, and this can be solved numerically with this air karma spectrum or air karma calculations. So we guess the thickness for the HVL, attenuate the spectrum in each bin of the each bin. So again, we can kind of use these bin values as monoenergetic values for different cross-section data. And then we calculate the air karma for this attenuated spectrum. If it's more than half, we increase the guessed width. If it's less, we decrease the width and iterate until we get this ratio close enough to 0.5. And just a note, for some reason, these HVLs from spectrometry are slightly smaller than from dosimetric measurements, so measurements with an ionization chamber, for example. And there has not been a good answer to this question why this is yet. And then, as discussed in the beginning, you can calculate these conversion coefficients from air kerma to dose equivalent also with the spectrum. So you start by calculating the dose equivalent in each bin of the spectrum. So a very similar procedure as for the air kerma by using these monoenergetic conversion coefficients given in the ISO standard. And after you have calculated the dose equivalent in each bin, you can calculate it for the whole spectrum by summing through the whole spectrum, and then you get this conversion coefficient by dividing this dose equivalent with the air kerma. And this similar procedure works with all of these different dose equivalents. You just need to use the right monoenergetic conversion coefficients. And the same procedure actually also works for effective dose from ICRP 116. And for all these other different things that you can do with the spectrum, the principle behind it is very similar. So you do mathematics for each bin of the spectrum and then sum or calculate some average over the spectrum. So, as a conclusion, spectrometry, it answers the, in essence, it answers the question, what is coming out of the tube, the X-ray tube? It allows determination of multiple quantities, and also you can use it for different research, detector development purposes, for example. There are a lot of different applications. But the problem here is that establishing the method is not straightforward. So you, in the end, need to do and learn quite a lot of different things: gamma ray spectrometry, pulse processing, dosimetry, Monte Carlo scripting, and so on. So pulling all this off requires a lot of resources, even though if you have someone that can help you from radioactivity or gamma lab, it helps quite a lot to have someone familiar with different spectrometers and spectrometry. But actually there is now an ongoing collaboration with STUK and ENEA, so the primary standard dosimetry lab of Italy, to re-establish this spectrometry method at ENEA. And one goal of this collaboration is to publish materials as open source, for example, examples of Monte Carlo model scripts that we used and different documentation. And the idea is that we, even though spectrometry is not easy, we could make it easier for others. And I will leave you with an open question that works as a good segue to Gavin's presentation. Could we, in the future, use simulated spectra instead of the measured ones? As you will see, this is for the end user quite a lot easier than measuring your own spectra. But thank you for your time.
Okay, well, thank you for the opportunity to speak. So Joonas has discussed the applications and the reason why you might want to determine a spectrum from an X-ray tube or X-ray machine. But I'm going to discuss a totally different perspective of what you can do when it's impractical to determine it experimentally, or if you just simply want to ask a kind of what-if question, trying to explore the consequences of something. So let's start. So that there are a number of approaches you can take to simulating or modeling what comes out of an X-ray machine. One option, using similar methods to discussed earlier, is Monte Carlo simulation. Now, this is perfectly possible, and it can be of two types. It can be a purpose-written code that for modeling X-ray tubes, or it can be something more general purpose, such as using the EGGS NRC or Penelope code systems, or several others, in fact. But there's also several other approaches. There's the analytical or deterministic models, in which, well, one approach is empirical. For example, if you have reliable experimental spectra at different tube potentials, for example, you could interpolate. And this is the kind of approach adopted by John Boone and his collaborators in a series of models called things like TASMIP and TASMIX. A more common approach is what is generally termed semi-empirical, in that they're a mixture of theoretical and empirical results built into a simplified model that describes experimental measurements well enough. And then I would say a third approach was a kind of theory simulation hybrid. And I'm making this distinct from semi-empirical in the sense that it doesn't have any parameters which are fit. So, for example, you might simulate the electron transport of the electrons in the target, and then use some theoretical results for the Bremsstrahlung part. It's not always clear whether a particular model is semi-empirical or theoretical, but it's a useful way to think about things. You often see these models referred to as semi-empirical, but the one I'm going to be concentrating on that comes from my own work, it can't really be considered empirical in the sense that nothing is fitted. And it's these analytical models which are most commonly used for the kind of quick and easy calculations, which are seen as practical and used in a variety of applications and software applications by people in universities and labs and hospitals around the world. Now, the starting point for these analytical or deterministic models, rather than modeling a whole X-ray machine with a generator, or even modeling the X-ray tube, really it comes down to considering a lump of metal, which you might consider is quite a crude approximation, but we can get quite far with this actually. So we have a lump of metal, most typically tungsten, that has an anode angle defined by the angle beta here, and it might be tilted. And these analytical models typically assume that you have no tube tilt, and that they provide predictions most commonly just on the central axis. As an input, you can often specify the anode angle. In fact, in most of these models, it's something which is sometimes called the takeoff angle that is most important. Now, this is the angle between the surface of the anode and the direction of the outgoing X-ray. And it's important because depending on this angle, it affects the thickness of the target that the X-ray has to pass through before it can escape. And therefore it determines what's called the self-filtration by the anode. And if you're using some software that has one of these models, and you determine the takeoff angle for your experimental beam, then you can input this as an effective anode angle, the sum of the tilt, the actual anode angle, and the angle that you are from the central axis. So to understand what's behind these models and why they work and why they don't, I'm going to just summarize some of the physics in a little bit more depth. As Joonas referred to, the electrons hit the anode with an energy proportional to the tube potential, and we'll assume that they all have the same initial energy striking the anode. But quickly, they're all going in the same direction as well. But quickly they scatter repeatedly, elastically, changing their direction. Now below here we have a plot. It looks a bit like the classic polar plot of Bremsstrahlung angular distributions, but that's not what it is. It's showing actually the distribution of angles of electrons at depth in the target when they penetrated to a certain depth. This comes from Monte Carlo simulations, actually. But right at the surface, at a zero fraction of the CSDA range, they're all traveling in the same direction, and that's depicted by this thick line on the axis there, all going at the direction of 0 degrees into the target. By the time it's gone just 3% of the CSDA range, it's still quite forward focused, but they're traveling in every direction. And as you go deeper and deeper into the target, you get a more diffuse distribution, which eventually doesn't change. But always there's more electrons heading into the target than heading backwards out towards the exit. Now, as well as changing direction, they're also losing energy through inelastic collisions. So they have a distribution in energy at any particular depth. So if you imagine choosing different planes at different depths in the target, if you choose the one at the surface, so the surface plane of the target, the electrons all have the same energy because they're just striking the target, and you have this like delta peak, which you see a proportion of 1 for their fraction of their instant energy. There's a little tail on it which comes from the backscatter of electrons out again. But as you go to planes at greater and greater depth, you get the mean energy of the electrons goes down because they've lost energy, and that they get a wider spread in energy as well. This is both due to stochastic energy loss and also the different paths which they took to get to that point and pass through that plane. So the result of this elastic scatter and the inelastic processes is that the electrons penetrate up to about half of their CSDA range, and in fact many electrons backscatter out of the target again, about 50%, so half the electrons scatter out of the target again in tungsten, and what happens to those depends on the X-ray tube design. But what I've got, this plot here shows it's on the y-axis, it's electrons per instant electrons, and its penetration depth as a fraction of the CSDA range on the x-axis. And what the y-axis means is if you take the fluence at a point, at a plane, at a depth in the target, and then you integrate over the lateral plane or positions, you get a unitless quantity, and that is electrons per instant electron. And as you can see from this, you have a peak at about 10% of the range, and then it's attenuated to be very low at by the time you get to half the range. So depending on the depth at which they emit Bremsstrahlung, we get different self-attenuations by the anode. And talking of Bremsstrahlung, this is what we're really interested in. And this makes up about 1% of their energy loss, although that number does depend on tube potential and the atomic number of the target. So these electrons are coming in, they're taking tortuous paths, they're emitting the occasional Bremsstrahlung, and we get these other processes as well, which Joonas also mentioned, the characteristic X-ray emissions. So the complicated thing with this is that there's two main channels involved. If sufficiently energetic, the electrons produce characteristic emissions in the target via electron impact ionization. So they knock electrons out of the atoms, and then we have atomic relaxations. But also, as well as that, the Bremsstrahlung itself, through this self-filtration we talked about, can be reabsorbed if it has enough energy, and that can result in further characteristic emissions. And these two different processes have different depth distributions. The impact ionization contribution is associated more closely with the depths at which the electron penetrates to, whereas because the other contribution comes from Bremsstrahlung, it can penetrate to a much deeper volume and a much deeper distribution of emissions. So we can see that even if we reduce what we're trying to model to a lump of metal, there's actually quite complicated physics going on. So let's discuss the limitations of these analytical models, because they evolved because people wanted quick and easy predictions, which were good enough, and but they make some quite big assumptions. The first order methods, which most of these semi-empirical models I would categorize them as, they make four big assumptions. They assume electrons penetrate in straight lines into the target. I say literally or effectively here because if you assume the electrons instantly reach a state of diffusion when they enter the target, then you can sort of effectively say that they move in a straight line, because for every one that scatters out, another one scatters in. You just have to correct for their path length being greater than their penetration depth. So that's not as dumb as it sounds, assuming they move in straight lines. But these first order methods also assume that electrons lose energy deterministically. So at a certain depth, they have a certain energy, not a distribution. As we've seen from the plots I showed, that's not true either. And I think as a consequence of these two assumptions is why there's this third approximation, the need to have fitted or empirical Bremsstrahlung cross sections. So this is kind of, if this is required, because if you have one, you need another wrong to average out the earlier approximation that you made. And also, in all these models, they assume that when you actually have a Bremsstrahlung emission, it's equally likely to be in any direction, regardless of the electron's direction, which is not true. But if you assume electrons are equally likely to be in any direction, then it actually, if that was true, it wouldn't make a difference. So these are approximations, and they're not necessarily stupid, but they are approximations and limitations to the model. My first adventure in spectrum modeling was with the model that is behind an application that is about 15 years old, SpecCalc, and this is what I would class as a second order model that used pre-computed electron distributions in the target from Monte Carlo, so it didn't make this second assumption, and I used a theoretical result for Bremsstrahlung cross section. So this was an improvement, but it's still assuming electrons effectively move in straight lines, and also that I assumed that they had a uniform Bremsstrahlung distribution. But recently we moved beyond this with a third order model, which is in some software that I'm going to talk about, SpecPy version 2. So this uses pre-computed distributions from Monte Carlo in the target for how deep the electrons get, how many get to what depth, what energy distribution they have at that depth, and what angular distributions they have at those depths. And then we fold in the theoretical results for both the Bremsstrahlung cross-section differential in energy and the angular distribution of the Bremsstrahlung. But what is SpecPy? It's a free software toolkit for calculating spectra. And because I would say it's this, I categorized it as third order, I'd say it's the most advanced physics model in any comparable kind of toolkit accepting anything that does full Monte Carlo treatment. And the code is written in Python, hence why it's called SpecPy. It's a toolkit rather than an application. So if you want to use it, you'll need to write or run simple Python scripts. So that can be a learning curve if you haven't used Python before. But fortunately, there's an extensive list of short example scripts in the online repository to get you started. So you can go to the Git repository and the wiki explaining how to use it at this URL here. So a little bit more on what you have to do. It's based on, well, you need to install Python, and the current supported version is Python 3. And you need a few standard libraries, NumPy and SciPy. Those are often even installed along with your Python installation. And then you need to get SpecPy from this URL. So assuming you've installed it all correctly and you've looked through the example scripts and run one, and then you want to get to you want to begin modeling your own beam that you want to have a predicted spectra for. So what information do you need as inputs? This is what you need to know. Firstly, you need the tube potential. Secondly, the anode angle. And thirdly, you need to know the thickness of filtration of the materials. There's a fourth one here, although it's optional, is the position to evaluate the spectrum. By default, it does it on the central axis at 100 centimeters from the focus, but you can specify an arbitrary position. A couple of notes here. Not everyone thinks about specifying anode angles or anode and tilt angles when they specify their X-ray beams, but actually it is quite important for accurate modeling. So if ever you are writing something with this in, then please remember to put that in. And also it makes it a lot easier for people who are trying to predict the spectrum. And another note, although perhaps this is the wrong audience to lecture on this, is that it's important to note that the filtration by air can be important for low KV beams. So we need to include this, and we might be surprised how often that is forgotten by users. So here is an example script. It's a bit longer than it needs to be to do what it does, but I will highlight a few key lines. When you write a Python script, you need to import the toolkit with a statement like this: import SpecPy. And then here is the real important business highlighted here. The first of these three lines, we create the spectrum model using this spec class. We give it as an input the tube potential and the anode angle. But what this does is it creates the model, but as it stands, it has no filtration, not even inherent filtration. So you need to add some. So that's what this next line does. We add 6 millimeters of pure aluminium filtration. And then on the third line, we use the get spectrum method to get our X-ray spectrum prediction. And it returns an array with the mid-energy bins and the fluents in that bin. And then I just highlight here for if you want to get other metrics out, you can, such as we've got methods to get the first HVL and the second HVL, the air kerma and the fluent. And I should note that by default, it gives you these answers at 1 MAS exposure and 100 centimeters. So here are the output of this script. It gives you the HVLs, the kerma fluents, and here's a plotted spectrum. So even though you do need to do a little bit of coding, it's only a few lines. And we have a large number of what we call methods to help you calculate various quantities like not just the ones we mentioned, but mean energy, effective energy, to get the thickness of a specified material to match a HVL, or you can make an arbitrary material based on chemical composition or composition by weight of different elements. And you can even input external spectra, for example, experimental spectra, and determine the HVL. I need to say a couple of words about the models in SpecPy. I've mentioned that it's what I'm concentrating on is SpecPy version 2. There was an earlier version. There are several models available for legacy reasons and for educational reasons, but the two main ones which we suggest most people should be interested in are KSIM, which is the default one, and KQP, which is the best, the highest accuracy model, which isn't the default purely because it's a bit slower. If you want to calculate at lots of different positions in space for a beam, it can get slow with the KQP model. It's much faster with the KSIM model. However, you know, it's still per point that you want to estimate a spectrum at, it's still less than a second typically with the KQP model. But also, if you use SpecCalc in the past and you want to emulate it in SpecPy, you can do that. So I've talked about SpecPy version 2 and 1 and the older SpecCalc program that I was involved in historically. How do these compare? SpecCalc slightly overestimates a spectrum in the high energy tip. It also doesn't include L lines, therefore it's inaccurate for lightly filtered spectra at low tube potentials. For example, the ISO Spectra H30. SpecPy version 1 includes L lines and generally provides pretty good HVL predictions, but it does overestimate even worse than SpecCalc in the high energy tip, and that's due to we improved a theoretical input, but SpecCalc it was rather successful because it relied on the cancellation of two errors. But neither SpecCalc nor SpecPy version 1 accurately model the anode heel effect, that is how the HVL or fluence change with different angles with respect to the anode surface. And they don't model the self-filtration of characteristic X-rays by the anode either. Whereas SpecPy version 2, we can model HVLs, fluence, and the heel effect accurately for both Bremsstrahlung and characteristic X-rays. And this is using Monte Carlo as a benchmark. And if you want the very highest accuracy, then, as I mentioned before, KQP is the option to choose. Here's an example for spec versus SpecPy version 1 and the KSIM and the KQP models. You can see that the dashed line SpecCalc has a little bit higher in at the high energy tip, and it also has no L lines, whereas SpecPy version 1, it exaggerates even more at the high energy tip. It goes above the other curves, but it does have the L lines, whereas the two models from SpecPy version 2 are essentially identical. And if we look at the HVLs in comparison to a nominal value from ISO 4037-1, we see that SpecCalc does fairly poorly because it's missing the L lines. SpecPy version 1 does better, but the other two models are both within 10 microns. So I would say that was pretty good agreement. And if we compare to a full Monte Carlo simulation of a simple geometry using beam NRC, we can see here on the right SpecPy's prediction in comparison to Monte Carlo. This isn't a normalized spectra, it's actually the absolute fluence spectra, and you can see it's a rather good agreement. But if we compare to some actual measurements of half value layer, what do we see? I've got from several standards laboratories. We've got from this Ankerhold report 18 IEC spectra, 29 ISO spectra, and this is using spectrometry, i.e. measuring a X-ray spectrum and then calculating the HVLs. And then I have 15 reference spectra from BIPM, and the same 29 ISO spectra as for the Ankerhold report, but as according to the NIST beams. So here are some box plots showing the difference between the SpecPi predictions based on the information I have from those references and some other sources on things like the anode angles and the filtrations and tube potentials. And you can see that the agreement for PTB for the IEC and the ISO spectra is of the order of sort of 1% with a fairly narrow spread. And we only have the HVL1s for these reference spectra for BIPM, but it's also, although it's a bit bigger shift from 0, it's still a very narrow spread. With the NIST beams, it's a little bit more, about 2 to 3% average difference and a wider spread with some anomalies. Quite the reason for that, I don't know, but it's one of those things, garbage in, garbage out. It may be that some of the assumptions I made as inputs were not quite correct. But you can see that we're typically looking at differences of a few percent. And here are the means and standard deviations in the differences here. So is this good enough? Well, that's for you to decide. It depends on the task. To put this in context, it has been suggested that the best estimate of filter thickness that can be achieved with reasonable effort is limited to 3% of the filter thickness, or 10 microns, whichever is greatest. So whether you agree with that number or not, it illustrates the point that whatever method you use, whether you're using the traditional dosimetry for measuring HVLs, or whether you're determining an experimental spectra in the way Joonas was discussing, and then calculating the HVL, or whether you're using something like SpecPi, there are uncertainties involved. You have to decide whether it's good enough for the task. And if you want to, I just want to say, if you want to match a HVL exactly, you can use this convenient function in SpecPi, which can give you an exact agreement. It can tell you how much material you need to add or subtract. But the HVL2 may not match exactly, or likely won't, but it should, as this is a pretty good spectrum model, it should be very close. Current limitations are that we have a narrow beam primary only here. This isn't going to change. We've had some people querying whether to add like contributions from characteristic radiation from the filters, but once you start having to model the size of beams and the locations of different components, you might as well do Monte Carlo. We have 3 types of target. We could add others. We have some interest in copper. It depends if people tell us they want something. And we assume tungsten is pure tungsten, which typically has a small amount of rhenium, but no one has mentioned this as a problem yet. We're going to expand the tube potentials a bit because it's limited down to 20 kV at the moment, and we assume 0 tube ripple, but we could model that if required. Currently, there's no graphical interface. You have to do a bit of scripting, as I said, but a web application will be available very soon, so you can do it in your web browser without doing coding. For more technical information, you can go to these papers, and for information on the toolkit and background information, there's a couple more resources. Other than that, I'll just slowly scroll through my list of references and acknowledge Robert Pagila, Arto, and Pedro Andreu for their contributions, and Massimo and Joonas for our discussions. And lastly, to CCRI for the honor of this invitation. So that concludes my presentation.